Hello everyone. This is lecture 10.4 of the GPU teaching kit. In this lecture, we're going to discuss more details about parallel scan.
The objective of this lecture is for students to learn more about parallel scan. We will analyze the work-efficient kernel, we will introduce exclusive scan, and we will also discuss how we can efficiently handle very large input vectors. We are now ready to analyze the work-efficient kernel. Recall that the work-efficient kernel has a forward phase and a back reverse phase. The forward phase performs log n iterations in the for loop, and each iteration of the for loop will do half n, quarter n, down to 1 addition. If we add up this series, it's a simple geometric series, and the sum is going to be n minus 1. Therefore, the loop is going to do order n work, where n is the number of elements in the input vector. Then we can go to the reverse phase. And in the reverse phase, the for loop executes log n minus 1 parallel iterations. And in each iteration, we would be doing 2 minus 1 equal to 1, 4 minus 1 equal to 3, and all the way up to n over 2 minus 1 additions. And we can sum up this series, and we will get, for the first part, n minus 2 is essentially the same as the first series, except that there's a missing 1. So that's why the sum is n minus 2. And then the second part, the minus 1 all the way will be, because we have log n minus 1 iterations and each iteration has a minus 1, the total of the subtracted term will be log n minus 1. By looking at this sum, we see that the work to be done is bounded by order n. So both phases perform up to no more than 2 times n minus 1 additions altogether. So the total number of adds is no more than twice of that done in the efficient sequential algorithm. However, the amount of parallelism can easily overcome the 2 times work when there's sufficient hardware. So this is why it is a work-efficient parallel algorithm. When we compare the work-inefficient kernel with the work-efficient kernel, we see an important trade-off. The work-efficient scan kernel is normally more desirable because it performs fewer number of operations. So fundamentally, it should have better energy efficiency, and it also has less execution resource requirement. So it's less likely the work-efficient kernel will have a slowdown when we have limited compute resources. However, the work-inefficient kernel could be better for absolute performance because it only requires the single phase, which is the forward phase. And whenever there is plenty of execution resources and there is no energy consideration, and we can actually have higher performance out of the work-inefficient kernel. Far, the parallel scan kernels can only work on one thread block because we need to load all the input elements into the shared memory, and then all the threads must be able to take the contents of the shared memory. So far, all these threads must belong in the same thread block. We're going to introduce a method that will allow multiple blocks to collaborate and process an input that is much bigger than what can be accommodated by the shared memory of a single thread block. And however, this algorithm is much better explained with the pictorial illustration in the next slide. And this one is just a summary of what we're going to explain in the next slide. This slide shows a pictorial illustration of the complete scan of very large input vectors. We take the initial input vector and we divide them up into sections and assign each section to a thread block. So the 0 section goes to block 0, section 1 goes to block 1, and so on. We perform a parallel scan on each section independently. So each section will have the scan value, but they will not include any of the values of the previous sections. And this needs to be completed in the next couple of steps. We will take the sum of each section, which is going to be in the last element of the section output. And this total of the section will be written into auxiliary array sum. This is shown in the middle of the picture. And then we perform a scan operation on the elements of the sum array. And this makes sure that now the sum array has the proper scan value for the positions at the end of each section. And then we add each of these sum elements to an entire section of the partial scan result. So by adding element 0, which is the sum of the section 0, to all the elements of section 1, we have completed the scan operation by adding the cumulative value of section 0 to all the elements of the partial scan result from section 1, and this completes section 1. The same way, when we add section 1 sum to section 2 partial scan results, we complete the computation for that section. So this gives us the final array of the scan values. Now we're ready to extend the concepts we learned from inclusive scan to exclusive scan. First of all, let's give the definition of exclusive scan. The first part of the definition is the same as inclusive scan. For a exclusive scan operation, it takes a binary associative operator circle plus and an array of n elements x0 through xn minus 1. The difference is in the way that it generates output array. The output array of exclusive scan start with a 0, and then it will be followed with all the inclusive scan output elements shifted to the right by 1 position. And the n minus 1th output element from the inclusive scan is actually discarded when we generate the output for a exclusive scan. That's why it's called exclusive. The last element is not used in the output calculation. For example, if the circular plus is an addition, then the exclusive scan operation result on the array of 3, 1, 7, 0, 4, 1, 6, 3 will be 0, which is the leading 0, 3, which will be is x0, which is 3, and 4, which is 3 plus 1, 11, which is 3 plus 1 plus 7, all the way to 22. And notice that this is the sum of 3, 1, 7, 0, 4, 1, 6. And the final element, xn minus 1, which is 3, is discarded in this calculation. Why do we want to do exclusive scan? The exclusive scan will find the beginning address of the allocated resources. If we go back to the sandwich, the inclusive scan finds all the cut points in order to generate the desired sections of the sandwich. However, in an exclusive scan, we calculate the beginning points of each section. So the 0 section will start at point 0, even though the first cut point will be at point 3. And in computer science and programming, when we use exclusive scan to allocate buffer memory, the outcome of the exclusive scan gives the beginning address of the sections of the buffer allocated to the individual requesters. So if we look at the example again, if for the input 3170, etc., the exclusive scan has the 0 to start, and then the elements 3, 4, 11, and so on. But the inclusive scan essentially will be the all the elements shifted by one position to the left, and then the final one is the total sum, including the last element of the input array. So the exclusive scan gives the beginning address, and the inclusive scan gives the cut point address of all the allocations. We can easily adapt an inclusive parallel scan kernel into an exclusive parallel scan kernel. For example, we can adapt an inclusive work inefficient scan kernel by having all the threads to load a input element that is shifted to the right by one position, and have thread 0 of the block 0 to load 0 into the leading XY element 0. Similar adaptation can be done to work efficient scan kernel, but we need to pay attention that each thread in that kernel will load 2 elements. So, but we need to make sure that only one 0 element should be loaded by thread 0, and all these other elements should be shifted to the right by only one position in the work efficient scan kernel. This is a very, very simple adaptation. However, there's a much more interesting and intellectually challenging approach to calculate exclusive scan from this without shifting the input elements, and this is detailed in the Harris article, Parallel Prefix Sum with CUDA. The interested readers should really read that algorithm. It's intellectually challenging, and it's actually very elegant. GPU programming. This is the end of the introduction to the toolkit. Thank you.